Assalamualaikum warahmatullahi wabarakatuh and salam sejahtera to everyone. I am KHADIZAH GHAZALI and today I will be presenting a research paper that I work on in collaborations with my colleagues. Our study, titled Accelerating Large-Scale Minimization Using Hybrid Block Newton-Aor Approach focus on problems with three-diagonal Hessian structure, will be the focus of this presentation. Let's start with the core problem for unconstrained minimization. In many applications, from machine learning to engineering, we need to minimize an objective functions, one that may depend on thousands or even millions of variables. For small-scale problems, classical method like Newton method work well. However, when dealing with large-scale system, this quickly becomes impractical. This leads us to the main challenge, that is computational complexity. First challenge is high dimensionality. As the number of variables grow, calculating second derivative, which is the Hessian matrix, become computationally expensive. Second challenge is the complexity of Newton method. As the size of the problem increases, solving large linear system involving the Hessian become resource intensive, requiring significant time and memory. And third challenge is memory limitation. As problem size increase, large-scale optimizations require efficient storage and management of data, especially when working with structure metrics like Hessian matrix. Given this challenge, there is a strong need for efficient optimizations method that can minimize functions with large three-diagonal Hessians. As we have discussed the problem and motivations behind our research, it's clear that tackling unconstrained optimizations problem opens up a range of possibilities. Beyond the specific context of our work, the method we are developing have broad applications. As shown here, unconstrained optimizations techniques have been successfully applied to areas like image restorations, portfolio selections and motion control, and even complex fields like DNA reproductions and neural networks. These examples highlight the potentials of unconstrained optimizations problem methods to solve device and impactful challenge across various domains. While our research focuses on a particular problem, the tools and solutions we are creating have the flexibility to be adapted and extended to many of these areas. In this slide, I briefly introduce the two main techniques used in our hybrid method, which is the block-Newton method and the AOR iterative method. The block-Newton method applies a divide and conquer idea to Newton method. Instead of solving the full problems at once, we break it into smaller blocks, which makes large-scale problems more efficient to handle. We also incorporate Marquardt approach to improve stability. When we are far from the solution, the method behaves like Stephenson, and as we get closer, it transitions to Newton method for faster and more accurate convergence. Finally, AOR or accelerated overrealization is used to solve large sparse linear systems arising from the Newton step. By introducing acceleration and realizations parameters, AOR converge faster than Gauss-Seidel and SOR, making it well suited for large-scale optimization problem. A three-diagonal Hessian matrix is a special case where most of the elements are zero, except for those on the main diagonal and the diagonals directly above and below it. This means the matrix has a very simple, sparse structure. In Newton methods, we rely on the Hessian matrix, which contains second-order partial derivative of the objective functions with a three-diagonal Hessian. Solving linear system become much more efficient because the storage requirement is reduced to just a non-zero elements, and solving the system of equation is computationally not expensive and faster, especially compared to a dense Hessian. This is another types of structure of the Hessians that we are applied for our project, but for this research we are only focusing on the three-diagonal form. We are working with the Hessian metric H1 and using the Marquard's approach to modify the Hessians, creating a new matrix HT1. The Marquard approach adds an adjustment term which help makes the optimizations process more stable, especially in difficult numerical conditions. After that, we decompose the matrix HT1 into three parts: D, a diagonal matrix; L, a lower three diagonal matrix; and U, an upper three diagonal matrix. This is known as the DLU decomposition. Finally, we use this decomposition matrix HT1 in linear system equation, which help us to find the next Newton updates. We break the matrix into smaller blocks of 2 points. By dividing the matrix this way, we can focus on smaller parts at a time, making the Newton method faster and more efficient. Then we can simply apply this to convert the n by n linear system into a 2 by 2 linear system. In this research, we consider unconstrained optimizations problem defined as equation 1, where the objective functions is moved with at least twice continuously differentiable. To find the minimum, we start by approximating the objective function in the problem 1 directly from the Taylor series using the first three terms of it, and since the approximation is a quadratic function, we can simply find the minimum of the approximations by differentiating it with respect to vector x and evaluating the resulting expression to 0. And by letting the new vector x as the new iterations, then we can have iterations with block-Newton direction, and this direction is obtained by solving a linear system in matrix form as equation 2. Since the matrix form we consider in this paper is a three-diagonal form, so obviously we can see that the characteristic of this coefficient matrix has large scale. Therefore, solving it directly is actually not a smart choice. So in this case, we decompose this Hessian matrix using the DLU decompositions by substituting the DLU decomposition into equation 2 and solve it, give the general form of this AOR method, which stated as equation 3 here. Equation 3 can be reduced into Gauss-Seidel method when omega equals with gamma equals with 1. While if omega equals with gamma, the equation 3 reduced as SOR method. And noted also that gamma is the acceleration parameter and omega is the overrealizations parameter. This slide illustrates the flowchart for our proposed algorithm. This algorithm involves two loops. The first loop focuses on finding the Newton direction using SOR point iterative method as the inner iteration, which is checked for convergence using the condition 4 here with adjustment to the Newton direction search, namely by calculating the norm of the difference between two consecutive Newton search direction iteration and terminating the iterations process by using the stopping criteria 10 power of negative 8. This choice of convergence tolerance is aimed at achieving more accurate result while minimizing the number of iterations required for convergence. Second loop, designed to find the estimated solutions for problem 1 using block-Newton equation as the outer iteration, using condition 5 here with 10 power of negative 6 as the stopping criteria. This selection is based on the suggestion of Andrea 2011, who stated that this choice is more suitable for terminating iteration in unconstrained optimizations problems. To validate and compare the performance of our proposed method, we use 5 different test functions. These functions are commonly used to evaluate optimization algorithm due to their various properties and challenges. First, we have Dickson and Price function. This function is known for its complex and multimodal landscape. Second, we have Rosenberg function, often referred to as the Rosenberg Valley or banana function. It's a classic benchmark for optimizations algorithm. Third, Nanscombe function. This is a lesser known but effective test case that presents steep, rigid, and sharp valleys requiring precise optimization. Fourth, cube function, a more geometrical sharp problem that helps access the algorithm ability to handle simple yet challenging forms. And last, we have straight function, similar to the cube function. This straight function evaluates optimization's performance in dealing with quadratic landscapes. All these functions were selected based on their Hessian structure, which has a 3-diagonal form. Each of these functions is evaluated with 3 different initial points, 1 standard initial point from previous studies, and 2 non-standard initial points that are randomly selected but close to the solution point. For each initial point, we run tests using 5 different order of Hessian metrics, 1,000, 5,000, 10,000, 20,000, and 30,000 order. The evaluation efficiency criteria are based on the number of iterations and the execution time. This table compares the reduction in inner iteration and execution time relative to the Newton-Gauss-Seidel. The results show that block Newton-Aor achieves the best overall performance with the highest reduction across most the test functions, confirming its efficiency for large-scale problems. And this table compares the total execution time and the speed-up ratio of our proposed block Newton-Aor methods against Newton-Gauss-Seidel, Newton-Aor, and also block Newton-Gauss-Seidel. From the result, we observe that block Newton-Aor consistently achieves the highest speed-up across most test functions, particularly for larger and more challenging problems. Let us consider test function 2a. Newton-Gauss-Seidel requires a relatively long execution time. By introducing AOR, the speed up increases, and when the block strategy is applied, the speed up further improves. In particular, block Newton-Aor achieves a speed up of approximately 7.5 times, highlighting the efficiency of our proposed method for large problems. This indicates that combining the block strategy with the AOR iterative scheme significantly reduces computational time, confirming the efficiency of our proposed method. As we conclude, the results clearly show that the block Newton-Aor method significantly improved the process of solving unconstrained optimizations problems, especially when dealing with a 3-diagonal Hessian matrix. This method doesn't just improve speed, it fundamentally accelerates the overall computational process, making it much more efficient. In addition, the block Newton-Aor method outperforms classical technique for computing the Newton directions. By offering a superior approach, it leads to significant improvements over classical method. This means better accuracy, faster convergence, and ultimately more reliable outcome for a wide range of optimizations problems. And here is the list of reference used throughout this presentation. Finally, we would like to express our gratitude for your attention. We also want to acknowledge Dana Cluster Penyelidikan UMS for their support in this research. Thank you once again for your attention.